Okie dokie. All right, I need to go download that thing because I don't have it.
I meant to put it in last night or yesterday, but I just totally forgot.
That's fine. That's way ahead of normal.
Oh,
Most people are
really?
getting these to me like 2 minutes before class starts.
That's funny.
Right? So let's see. Astrobytes, astrobytes, astrobytes. It's gone. It's gone. There you are. Oh, missed it. There it is. All right. Let me. Oh, I got a background. I forgot about that. Hold on. Let me change my background.
No, it's okay. I like it.
You like that background?
Yeah.
I'm going to leave it for now?
Yeah.
I'll leave it for now. Okay. Okay. Let me close this.
Cool background. Kind of fits in.
It does kind of fit in, doesn't it? All right. Give me 1 minute to run down to my office and grab my notes, and then I'll.
Yeah, I was like, for, I didn't myself there. PowerPoint. You got 15 minutes. I feel prepared because of it.
I didn't feel prepared, but I feel like this one didn't go a lot more.
I feel like that. I don't want you to get so much of do 15 minutes. Don't be like a time. Turn it all up. Yeah. Be like, am I over?
Okay.
Let me pull these guys, make it a little easier to see. Take it away.
All right, so today I'm going to be talking about the influence of magnetic fields on H2 regions and star formations. So the first thing we're going to talk about is balloons, quote unquote. So as young stellar objects, also known as stars, heat up interstellar materials, the stellar winds and UV radiation expand outward, expanding the H2 regions. And this creates what they call the balloon of interstellar materials surrounding a star. And this changes the magnetic field around these stars. So what the authors of this article took a look at are the star-forming complex called S235. And this is just a big picture of the star complex. And in here you can see 3 different H2 regions. The big one, S235 main, and then the 2 other smaller ones, S235AB and S235C. And this just shows a picture of what they're calling these balloons, quote unquote. And in there you can see the green stuff are all the stars all around, and then they also show the center of each balloon. So what they want to do, they want to find the magnetic field of these balloons. And to do that, they use whatever that word is, polarimetry, whatever, how you ever say that.
Polarimetry.
Yeah, there you go. Polarimetry from Mamier and Poliquin. And these are 2 instruments that are used for imaging. Mamier is from Lowell Observatory, and
The Lowell Observatory.
Lowell, and its uses are imaging, spectroscopy, polarimetry, and then Polican is a near imaging linear polarimeter. There you go. That is also attached to a near imaging camera. And then with these two instruments, they're able to measure the orientation of light from the stars. So the polarization of this light gets changed by the dust grains, because they will align their axes perpendicular to the magnetic field. So this causes certain light to be blocked by the dust grains, giving us an orientation that they can trace for the magnetic field. But there's also polarization from other objects like the stars in the background and the young stellar objects in the balloons themselves. So to clean up some of the data, they use Gaia distances and the amount of dust present to filter out foreground stars. And then they also threw out polarization data from these other stars, young stellar objects. And then to make sure that they were getting the right polarization, they subtracted the average polarization from the foreground stars from the stars in the background. And then that left them with these yellow lines of the magnetic field. So the longer they are, the stronger it is, and the direction is the direction of the magnetic field. And from this, they concluded that the magnetic field, as the H2 region expands, the magnetic field actually shrinks, which is kind of weird. But so the conclusion that they found from these magnetic field lines was that at a certain point, the magnetic field actually got strong enough that it stopped the star formation in the H2 regions. And from this, they had concluded that star formation had to have happened in the past because there's stars in the H2 regions. And then they finally concluded a sequence of events. First was that magnetic field and the gravity balanced out, which caused stars to form. And then as stars formed and the H2 region expands, the turbulence decayed and the magnetic field halted formation. And that's really it. References.
Question.
How is dust oriented in polarity?
I don't know. I honestly really don't know. I was very confused with that too.
Yeah, this is all very complicated stuff. I don't really understand it myself. But, you know, the daytime sky is polarized, partially, because of dust grains in the atmosphere. So it probably works similarly in the ISM. So, I mean, it's not polarized if you look right at the sun. Don't look right at the sun. If you do, it's not polarized. But it's polarized kind of at 90. So if you take out your polarized sunglasses on a sunny day sometime, look around because it's really interesting. Some parts of the sky will be dark and some parts and as you turn your head, it will actually change which parts of the sky are dark, which parts aren't dark. And it's about 90 degrees. So if you look 90 degrees away from the sun, those are the sunlight's reflecting off of those dust grains, and those are the particularly polarized ones. So dust grains will polarize light as it reflects off of it, and I think that's what they're doing here.
Okay, sure.
And I think the magnetic field will align the dust grains in such a way. So
Great.
I don't really understand it, but
I looked at it a little bit and I was like, I have no idea. But yeah, the only thing it said was that the dust grains block light from
Right. I mean,
background stars.
like with that phenomenon, it's like if circularly polarized light becomes linearly polarized when it's reflected on 90 degrees. But then if these dust grains are between us and those stars.
no, I think they're mapping out the magnetic field in the nebula itself. So these are dust grains that are in the
Yeah, it's in the H2 region.
Okay, sure.
that are reflecting the starlight from
Okay.
from the sample stars. Cool. Thanks, Tom. Say this has been an excellent Astrobites semester. Like there hasn't been a dud in the group. Give yourself a round of applause for excellent Astrobites this semester. Well done. Great. 2, 4, 6, 8, 10, 11. We're missing a few. And nobody's tuned in, I don't think, on Zoom. And I am. Let me take away the background because that's going to be weird and you're going to be able to see the board. Okay. And let me make sure that, yeah, we're doing the right. Okay, great. There's a pup date and an astro and an astronomy picture of the day. Thanks for reminding me. I wouldn't want to forget that on the last day. I haven't even looked at today's APOD. What's it going to be? Was it? Oh. That looks like Australia and, yeah, Uluru, which used to be known as Ayers Rock, but that's so Western. Yeah, look at that. Australia, yeah, there's Orion. You know, anything problem with Orion? It's upside down. There's Betelgeuse, there's Rigel, there's the belt, there's the. So I actually went to grad school with an Australian grad student, and he was like, your Orion is way wrong up here. He is upside down. He could not handle Orion the way it was seen from here. And now I can see how he saw it, but that's clearly wrong. I mean, obviously.
Doesn't it look like that when it's visible in the summer, like really early in the morning?
No, it's sort of on its side, so it kind of rises in the side. I mean, when you see it in the horizon, it's either right side up or he's on a side on either side. You so really have to go, you know, do like this to see him upside down from here, and you don't really do that normally. Yeah, that's fun. I hear yesterday's was nice too. I didn't check that out. Ooh, look at those beautiful star clusters. That almost looks like M35. These M35. These are my two favorite star clusters. I picked it out. Isn't that amazing? I have studied these two star clusters rather extensively. This is one of my thesis clusters. A very rich, look at all these beautiful blue stars, rather young, like 150 million year old cluster that is pretty nearby. What?
150 million year old?
Yeah.
Like, okay. That's way under the stellar age than what we seem to be exposed to.
Way younger, you mean?
Yeah.
Yeah. This is a pretty young cluster. Yeah. So that's exciting. And then in the background, there's an even richer cluster that's much further away, but this is also an open cluster. One of the richest open clusters I've ever seen. Like, look at how many stars there are in that cluster. It looks like a globular cluster almost. There are so many stars there. But this is 2158, an older cluster, much further away, but still useful and interesting because there are just so many stars there. It's rather exciting. What a great picture of M35 and 2158. That's fantastic. Okay, cool. Pup date. Let's see what the puppies are doing. Puppy Palooza was great. Sorry, not everybody got to be there, but it was well, you know, it was wet and muddy and rainy, but it didn't really stop the puppy enthusiasm, I don't think, which was nice to see. Where are the puppies? Oh, that's not it. Yeah, it's about normal. There, I don't have my video on. Yes, I do. There it is.
Is this a new perspective?
I don't think so. This is looking like maybe we moved the camera a little bit, but that's about it. There's the puppies. So yeah, they thoroughly enjoyed the weekend. They were completely tuckered out after playing with people for the afternoon. That was nice. And this is the last week we have them. They turn 8 weeks on Thursday. We take them up on Saturday to have meet and greets with potential adoptees, and hopefully they all get adopted, and we'll only keep the one that we're keeping. So that'd be nice. So yay. You probably want to know about the final exam. I should give you some deets about that. I did some investigating and I did some thinking, and here's how it's going to work. It's actually different than I was saying before. So it's going to be a CAPA, open book, open note. It will be a 2.5-hour exam that will start at 12 noon on Monday and be over at 2:30 on Monday afternoon. It will be open note, open book, open all resources except for collaboration. You'll have access to Mathematica, and it will feature problems that you've seen before. Well, not exclusively problems that you've seen before, but mostly problems that you've seen before, either on the homeworks or on previous exams. So come organized with all of the old stuff you've done this semester, prepared and ready to go. It won't all be old stuff, but it will be a decent amount of stuff you've seen already this semester. It will be cumulative. It will cover the whole semester, which is different than I said before. But I think the open note, open book part of it will make up for that. Question?
It'll be in here, but on CAPA?
No, I think what we're going to do is probably set up in the astronomy and analytic labs and just give yourself more room to spread out and not have to feel like you're.
But we will actually be coming to the ISC, not just.
You will be coming to the ISC and doing it here. That's right. That's right. It will be an in-person, open book, open note. But yeah, in the lab, so you have enough room to spread out and things. Other questions?
Is it gonna be like 2.5 hours of stuff?
I think it will probably take some people 2.5 hours. I don't think it will take everybody 2.5 hours. That's my goal.
Is it likely that we'll have to like plot stuff, or
You may have to
will it just
plot.
be, like maybe some matching ones?
You may have to plot stuff. That's a possibility. It's certainly fair game. Speaking of plotting stuff, I hope your projects are coming along well. Come and ask me questions. Some of this stuff's confusing and hard to do. I'm happy to answer questions. I've already answered dozens of questions from people, so don't feel bad about coming to see me about questions for the project. And if you need an extension, I have still I've yet to say no to anybody who's asking for extension this semester, and I probably won't start now. So just be aware. Okay, any other questions about end of semester stuff?
Well, never mind. I was gonna ask if there would be a update for the final, but the puppies will be gone.
The puppies will be
That's so
gone.
sad.
Maybe you'll have some pictures from the meet and greet, but
Just have like a slideshow of puppy pictures.
slideshow puppy pictures. That would be nice.
Older dogs.
A dog date. Okay.
Frisbee getting nudged towards.
Yes. Right. Okay. Great. So what do we have? A half an hour left in this class. I'm not even sure I'm going to use it all. We'll see how far we get today. So we're talking about neutron stars. And I think that we had just talked about how a neutron star was basically a nucleus with A equals 10 to the 57, and Z something like probably 10 to the 55, right? So what the heck? That's well beyond our end of the periodic table elements. I don't think we have a name for that because it's kind of ridiculous to even talk about the chemistry of such a thing, because there would be no chemistry of such a thing. So let me share this again, and let me bring up and oh yeah, this is our picture of a neutron. I like this picture of a neutron star over Vancouver. Obviously, this wouldn't be a picture that could last for very long because the neutron star outweighs the Earth by a factor of 10 to the 5 or something, and so the Earth would very quickly become part of the neutron star.
It's kind of crazy to think that.
Yeah, the gravity is definitely pointing in the up direction in this picture, and it's not even close. Right, 1 G down. What did we say? 100,000 G? No, that was a white dwarf. I don't even know. Some ridiculous number of G's up. Okay, so is there a Chandrasekhar mass limit for a neutron star, the equivalent or so? Yes, the answer is yes, because neutron stars behave, you may remember, very similarly to white dwarfs. Again, this is just Chandrasekhar mass limit is for white dwarfs. We don't call it the Chandrasekhar mass limit for a neutron star, but if we were to call it, it would be something like that. Again, the upper limit for a neutron star, they work the same way. Degeneracy pressure is degeneracy pressure. Basically, it's just a much denser state. And so the more massive you make these things, the smaller they get. And then you get into relativistic effects. And the plot for radius as a function of mass for a neutron star looks very similar to that of a white dwarf. It just curves over and it goes to zero at some point. So detailed models actually give a range of possible upper limits of mass. There's no 1.44 solar mass number for a neutron star, interestingly. Partly because we probably don't understand the physics quite as well in neutron stars as we do in white dwarfs, but also because these things can be spinning very fast, and that rotation actually can affect the structure of the neutron star and how massive they can get. So detailed models suggest something like 2.2 solar masses for non-rotating neutron star, but I'm not even sure such a thing exists. It's probably not possible to have a non-rotating neutron star. Probably all of them are spinning at ridiculously high rates. And if you spin this thing, it can get up to like 2.9 solar masses for a rapidly rotating. That's a pretty substantial difference, although we're probably more into this range than we are into this range for the vast majority of neutron stars out there. Usually you'll hear people say something like about 3 solar masses is the upper limit for a white dwarf or a neutron star. Well, it's possible you could fail before you get to 3 solar masses if you're not rotating fast enough. But it's a much more fuzzy number than the Chandrasekhar mass limit. So what happens when you get an object, a neutron star, you dump enough mass onto it that it exceeds this upper limit for the mass of a neutron star? It must collapse then even further, smaller than that. And at this point, neutron degeneracy pressure was the last hope that this thing had for holding itself up against gravity that we know of. We know of no physical mechanism to keep this thing from collapsing to 0 radius. We know of nothing that can hold this thing up at this point. Where the neutrons go, I don't even know what the physics happens of, I could tell you the physics of where the electrons go when things collapse in a neutron star. Where do the neutrons go when it collapses below this? I don't think we know, and I don't think it really matters. This is the interesting thing, because what does that thing become as soon as it collapses from a neutron star? It becomes a black hole. Once the thing shrinks below its Schwarzschild radius, and the Schwarzschild radius is defined to be the region around the black hole that is infinite curvature in the GR sense, or has an escape velocity equal to the speed of light, if you want to think about it in the classical sense, then you've lost all communication with that thing. You cannot observe anymore what is going on inside the surface of that thing. And even for a 1.5, 2 solar mass neutron star, its event horizon, its Schwarzschild radius, is not that far inside of the surface of the neutron star itself. So it's possible that even before you get to this point, even while it can support itself by neutron degeneracy pressure, it's below its outer radius is below its own Schwarzschild radius, and it's become a black hole anyway, and you can't actually observe it anymore. So I'm not going to get into the physics of black holes, partly because I'm no GR expert, and partly because we only have 25 minutes left in class. And obviously that's a topic that deserves much more time than that. But Who's all taking the GR gravity class?
It's a small class.
Have you talked about black holes? I assume that's got to be a topic you cover.
Yeah, just.
Yeah, we did a bunch of stuff with the Schwarzschild metric, and so we talked about them.
Right.
And then we got briefly into spinning black holes, and I got very lost.
Yeah. Right. So like spinning neutron stars, it's probably not possible to have a non-spinning black hole, but they're a heck of a lot more complicated to think about than non-spinning black holes. So usually you save that for a graduate level class, but good for Dr. Iyer showing you the real stuff. Not that I've ever had a GR class. So the stuff I know, I've read in intro textbooks or been told in various random classes along the way. So you get another collapse. No known force can support it. And you get a black hole. And black holes are really interesting objects. Again, there is the event horizon of a black hole is that region around the black hole where the curvature becomes infinite, and you get all sorts of weird singularities happening in GR stuff. But it's also an information barrier. No information can leave from the inside of a black hole. And so there's really only three things you can measure about a black hole because they affect the space-time outside the black hole. That is the mass of the black hole, that is the charge of the black hole, and that is the spin rate of the black hole. Those are the only three things. You don't know what it's made of. You don't know what its color it is inside there. You don't know anything, any physical thing that's happening inside there is unobservable by the rest of the universe. So that's weird. These things also have to be rotating really fast. There's a problem on the homework set where you examine the angular momentum history of a black hole or a neutron star as it collapses from a white dwarf. Angular momentum must be conserved. I'm thinking not of this collapse, but as you know, you make these things by collapsing down something that was electron degeneracy pressure supported, roughly the size of the Earth, down to something that's the size of Vancouver. That's a very large change in radius. And so as you collapse from white dwarf, you've done this problem already. But you basically get, I'm gonna skip some of the intermediate steps. The angular frequency of the final state after you've collapsed is equal to the angular velocity of the initial state times the initial radius divided by the final radius squared. And this is on the order of about 500 to go from the Earth down to Vancouver. And 500 squared is a big number. And this can be, 250,000, on the order of. So the rotation rate can increase by a factor of 250,000 from the white dwarf state down to the neutron star state. So even if you weren't spinning all that fast, that thing sort of has to be spinning fast. There's no other way around it. This works the same way for the orbital periods. Oh, look, there's a clock here. Do I care? Not really. Final periods of a neutron star, again, initial periods related to the rate, since periods related to frequency by the inverse, you just switch the RS and RIs. And this goes up by a factor of 200,000, or goes down by a factor of 1,000 instead. So, you're getting rotation periods as low as, a millisecond. right? This whole thing is spinning so fast that it can make one complete spin 1,000 times. It can spin 1,000 times per second. It's kind of hard to even. I mean, everything about this is hard to wrap your brain around. That's another one of these numbers that's just sort of impossible to think about. Even as something as small as a neutron star can't spin much faster than this, even because even at something like this period for a neutron star, the equatorial rate, the points on the equator are traveling like half the speed of light or something, just to be able to do that. It's even neutron stars can't spin much faster than that, or they will spin themselves apart even at quadrillion Gs.
Though at that kind of linear velocity, isn't there locally perceived distance travel much shorter?
Yeah, you get all sorts of weird relativistic effects with these things. Not only the special relativistic effects from those, but these are curved paths, and you've got obviously a rather large amount of curvature, space-time curvature here. So yeah, thinking about this classically is not the right way to do it, because there's nothing classical at all about what's going on here. I don't really understand the physics well enough to be able to give you any insight about how that works, but I certainly know that it's wrong to think of it just purely classically. Let's look at some other cool pictures. Aha! So these things have actually been discovered, and they get discovered as so if you've got the spinning pulsar. It's spinning neutron star, and it's spinning obviously with a rotation axis that looks like that, and it's spinning really fast. And you have some things, maybe there's an accretion disk around this thing that's feeding matter onto it. The other thing that happens when it collapses from white dwarf is the magnetic fields there isn't a lot of charged particles left because mostly neutrons, but there's still 1% or 0.1% protons and electrons that are enough charged particles that will drag the field lines with it. So the magnetic fields of this thing should be also really, really strong because all those field lines get drugged out. And what happens typically is just like the Earth, the magnetic field axis and the rotation axis aren't perfectly aligned. And so you might, at an instant of time, have a magnetic axis that's over here somewhere. Let's just draw in some field lines. You get the idea. This is a bad dipole, but you get the idea. And what happens is, as material is accreting onto this thing, it can't cross these field lines, and the material gets directed along these field lines to the poles, and some of that gets shot out in jets, typically that are emanating from the magnetic poles of these objects. And again, the magnetic field is really, really strong, so these charged particles will spiral around, and they'll emit. And accelerating particles emit radiation, and you'll get radiation, light moving in that direction, and light moving in that direction. And so these things are kind of like beacons. They're flashlights shining in the direction of the magnetic poles. And as this thing's spinning really, really fast, those flashlights are spinning really fast. And if you happen to be over here looking at it, far away, well, right, not to scale, really far away, you'll get a flash of light. This thing will be spinning around, and you'll get a flash of light every time this thing goes by you, kind of like someone swinging a flashlight, and you just see a pulse of light every time it goes by. We call these things pulsars. They don't pulse. Pulsars, Cepheid variables are pulsating stars. Pulsars don't actually pulse physically, but we do get pulses of light from them every time one of these things flashes around. Who were they discovered by?
Jocelyn Bell.
Whom you've met at a AAS meeting. So she was a grad student. I don't know the full story of the discovery, but she kind of designed, this is hard to do, right? These are sub-second flashes of radio light, really, from these things. I'm not sure she was really looking for these things, but she had the idea to look for. It's usually hard to find these things, right? Because to see faint things, you have to go to the telescope and integrate the light for like a minute or two, right? And you just get the average light over that minute, and you're going to miss if something's blinking on and off really fast. So you have to design a very clever experiment that's going to be able to tell whether something's something's flashing on and off that fast. I don't remember exactly the details of how she did it, but she had the idea, designed the experiment, and this is, I think, the log from her notebook in 1967, where she actually sees these pulses of light coming from this particular object that she was looking at. So she's the first person who's ever discovered pulsars and by extension neutron stars. First person to ever observe them and notice from what they were. One of the tragedies of the Nobel system, her PhD advisor won the Nobel Prize in physics for this discovery like 2 years later, and Jocelyn Bell did not get any credit for it in the Nobel announcement. And I don't even think his advisor even thanked her in his speech or anything. So it was sort of discovered years later that she had done most of the work for this project, and then people were outraged, but it was kind of too late to take it back at that point. So anyway, a story of Nobel injustice. There's no shortage of them, but this is this is one of the more egregious ones. So she deserves some love here. 1967, pulsars are observed. So these things are cool objects in themselves. This is a histogram of all the periods of all known 1,533 pulsars as of the printing of the book, probably in the early 2000s. We probably know more about them at this point, but I'm not guessing that period, this histogram, is going to change much. But it's an interesting dual mode period, dual mode histogram. Clearly, this is a log period in seconds, so this is going from 10 down to almost, it's a -3 would be 0.001. That's sort of the limit of how fast you can go, because it's the limit of how fast you can go before these things can't really spin any faster. But you've got a nice peak of them here at a little bit less than a second, a peak that is right around a second. So a second is included in this. And then another peak at less than a 100th of a second. So between 100th and 1,000th in the millisecond range, in the single digit millisecond value range, which would be these guys down here. So that's interesting. I'm not sure, maybe there's some physics involved here that I don't know about, but I thought this was an interesting plot. Oh, here is a better drawing of what I've tried to do here, showing the pulsar. You've got the spin axis, you've got the magnetic axis, you've got the emission cone where these charged particles are spinning around and emitting light in that direction. And if the Earth happens to be in this line of sight, we're going to get pulses of light every time it goes around. Right. This is even better than the magnetic field lines. Not that my magnetic field lines are bad, but this is kind of better. Oh, light cylinder. I don't know what they're talking about here. Again, I'm not an expert on this stuff by any means. So I have no idea what that means. Here's an example of a picture of a pulsar. It's kind of hard to see. It's way down in the center here. This is the Crab Nebula. This is a supernova remnant of a supernova that was recorded to have gone off on Earth in about 1054 AD. And this is what the supernova looks like today. The remnant looks like today. Obviously, supernova goes off, huge cloud of expanding gas that can glow for hundreds, thousands of years because there's so much energy being involved. But at the center of this thing is a pulsar. And one of these things, and I think it's in the millisecond pulsar range. It's like, no, it's not. It's 30 times a second. It spins 30 times a second. So it's in the 0.033, which would be down like here somewhere, I think. It's sort of in the middle of the valley between these two. It's one of those weird ones. Anyway, probably because it's not that old, right? I'm guessing these are the young ones, and then they evolve over here with time as they slow down, but I don't really know how that works. Anyway, this is a picture, a blown in X-ray picture of the center of the supernova remnant, and that's the pulsar itself. You can see the jets and the accretion disk and the things that I was talking about.
So that's just what's left of the star. Is that?
Yeah, that's what's left of the star. Yep, this spinning core. just doing us damage, not doing us so much damage. Okay, how does I think that's the last of my slides. What is the temperature of a neutron star? This is also kind of interesting. When it's first created, and again, neutron star structure is pretty similar to white dwarf structure in that, T about constant in the middle, and there's like a crust on the outside where it's an insulating crust that is obviously cooler as you go out because it has to be in thermal contact with the outside, but keeps the center part, the French onion soup analogy, again, holds reasonably well here. You've got an insulating layer of cheese on the top that's, kind of cool to touch compared to the inside that stays pretty hot because of that with a crust. So when I say temperature of a neutron star, I'm really thinking about the interior of the neutron star.
You indicated earlier that we can effectively treat this as a singular nucleus, though, right?
Yes.
And most of our discussions of temperature, we don't talk about subatomic particles bumping into each other.
That's true.
We talk about.
That's true. The equation of states of neutron stars is a weird topic. And I don't have, you'll eventually, you'll go to an astronomy conference and you'll see, a whole session on equations of states of neutron stars. I've never gone to one of those sessions. One, because I'm not that interested, and two, because I probably would understand 0% of things that they were talking about. But it's a weird thing, right? Because you've got the strong nuclear force, obviously, that's playing a major role in how these particles are interacting, but there has to be some gas dynamics that goes on too. It's not just an atomic nucleus. There has to be some gaseous elements to it. So
I imagine you're removing all of the dual repulsion, so it's only just collisions.
Right. It's collisions. It's physical collisions. You do get some cooler repulsions at some level, but it's probably strong nuclear force collisions, right? That's what's causing these things to collide, rather than the Coulomb force that's causing these things to collide, right? But it's a collision, right? I don't think it matters what that repulsive force is, as long as there's a repulsive force from these things.
They get much closer together because of it, and then they probably get repelled.
Exactly. So there's a push and a pull, but they're not allowed to get that far away from each other anyway. So because they're in there so densely, so. It's a weird, the equation of state of neutron stars, again, is a weird thing to think about. And there are very smart people who think about it. And I don't think there's no way to test it either, right? You can have these theories, but how do you even, there's no way to simulate the conditions inside a neutron star on Earth, I don't think. So we're kind of guessing. We're kind of measuring something and making extrapolations towards what the conditions might actually be like.
When we're simulating gas or simulating gases, we have to keep track of things like electric fields and magnetic fields.
Right.
In this situation, it's mostly neutrons.
That's true.
So,
you don't have to. But there's other things you have to worry about that you don't have to worry about in normal gases, like, like the strong force, for instance, and
forces that we don't necessarily have as much.
Right. Yeah, and yeah, you've reached the depths of my understanding of thinking about the gaseous states of neutron stars. You can probably read about it, but I'm sure Bob has a whole section on equations of state of neutron stars at a probably digestible level. I have never read that section of Bob, and if I have, I've forgotten it all. But feel free. I'm sure it's interesting.
You probably don't get to use the Boltzmann constant anymore. Well, you definitely don't get to use the Boltzmann constant anymore.
Yeah, probably not, but I don't know. It's a good question. Anyway, when they're first created, these things are hot. T of about 10 to the 12 Kelvin. Like that's, you have to go to the beginning of the universe to find anything that's hotter than that, I think. This is sort of as hot as it gets in normal astrophysical contexts. So that's really hot, but this doesn't last very long. So it cools by neutrino emission. Which is weird to think about also. neutrons decay into protons plus electrons plus anti-electron neutrinos, and then these guys simply can't be around very long. So P plus E minus goes back to neutron plus a regular electron. So these things are probably happening constantly, transferring back and forth between one another and emitting these anti-neutrinos and regular neutrinos, and that carries energy away and cools this thing off fairly quickly. In fact, very quickly at the very beginning, according to the, oh, come on, buddy. There you go. According to the textbook, do it. According to the textbook, after 1 second, the temperature is gone down to about 10 to the 11th. So it drops by an order of magnitude in a second after it's created. It just doesn't last very long. And then after about 1 day, temperature has gone to about 10 to the 9 Kelvin. And then a few hundred years, it slows down, obviously, about 10 to the 8 Kelvin. So this guy's probably at the center, about 10 to the 8 Kelvin. Now, the surface, this crust, is much cooler, but still really hot compared to anything else we've been talking about. Maybe 1,000,000 Kelvin at the surface, right? And that is, you're going to get a black body spectrum of this thing that is 1,000,000 Kelvin object, right? It's not going to have much, there's not going to be any hydrogen on the surface of this thing. You're not going to get Balmer lines. It should be a pretty good black body spectrum, I think. But at 10 to the 6 Kelvin, well, what's the luminosity of a 10 to the 6 Kelvin object that's that small? We have all the information. We know its radius and we know its temperature. We can calculate the luminosity. 4 pi r squared, sigma g to the 4th. If you remember one equation from this class, it's probably going to be that one. It's an important one. You plug all those numbers in. I don't know how time you roll from alpha, but you get about 7 times 10 to the 25 watts for a 10 to the 6 Kelvin object at about 10 kilometers in radius. That's pretty bright. That's about 20% the luminosity of the sun. So why are these things invisible? It's because these guys, most of this is going to be in the X-ray. These guys are so hot that the Planck distribution peaks in the X-ray part of the spectrum. And the visible luminosity is going to be extremely small. Almost nothing's coming out in visible photons. Peak wavelength. Remember, lambda. This is like astronomy's astrophysics is its greatest hits at the very end. Lambda max equals 2.9 times 10 to the 6 nanometers kelvins divided by T. You get about 3 nanometers is where this thing is going to peak. 3 nanometers, right? Not 300 nanometers, which would be in the UV. 3 nanometers is squarely in the X-ray regime. And it's very faint in the visible. You're not going to get any visible light photons. So they weird things. All right, that's all I got. I ended 1 minute early. You're welcome. If you don't mind, go fill out the selfies. This has been a weird semester. You know, I'm tenured full professor. None of this really matters anymore to me on a score level. No, let me explain. I don't care if I get low scores anymore. I do care what you liked and didn't like about this class. I do care about making the class better for future generations. So I do appreciate the comments. If you do have the time to go out and fill one out, I'd appreciate it. So thank you. You're welcome.
This was a very fun class.
Hey, I'm glad you liked it. That's not what I said.
I don't need printer balance anymore.
Quote Steinhauer.